everyone, my name is Aparna Sheji and today I am going to take the seminar on the topic Neuromorphic Engineering under the guidance of Assistant Professor Sanju Sebastian. So, before entering to the introduction, what is neuromorphic engineering? Basically, neuromorphic engineering combines neuroscience, electrical engineering, and computer science to create artificial neural system that mimic the structure and the function of the brain. The term neuromorphic is derived from neuro, meaning relating to the nervous system, and morphic, meaning structure. These are the contents. Introduction, history of neuromorphic engineering, what is neuromorphic computing, neuromorphic hardware, artificial neural network, work related, advantages and challenges, applications, companies related to neuromorphic engineering, future scope, references and conclusion. So let's move on to the introduction. As I already said, it is a field of study that draws inspiration from the structure and functioning of the human brain to design and build artificial systems, particularly electronic circuit and systems. The primary goal of neuromorphic engineering is to create systems that can mimic the way the human brain processes information. It can perform the task more efficiently and effectively than traditional computers. In this diagram, as you can see from the first diagram shows a history of Google searches of the term neuromorphic engineering. It can be seen that there was a decline in interest about neuromorphic research around 2010. And figure 1b is obtained also by analyzing the number of papers published in relevant journals from the Nature Journal series over the last 10 years that are on the topic of neuromorphic research. Let's dive into the history of neuromorphic engineering. The evolution of neuromorphic engineering has been marked by significant milestones and advancements over the years. This brief historical background provides a glimpse into the evolution of neuromorphic engineering, a discipline poised to reshape the landscape of intelligent computing. So, during 1940s to 1960s, early theoretical foundations was occurred. The foundation of neuromorphic engineering can be traced back to the work of Warren M.C. Culloch and Ward Rapids in the 1940s. They introduced the concept of artificial neurons, which served as the building blocks for neural network models. In the 1960s, Frank Rosenbold developed perceptron, one of the earliest forms of artificial neural networks. It gained attention for its ability to learn simple tasks. During 1970s to 1990s, this contained connectionism gained prominence and emphasizing the interconnected nature of neurons in neural networks and exploration of parallel processing capabilities in artificial neural networks. In 1990s, witnessed a resurgence of interest in neural networks and their potential for solving complex problems, and the development of backpropagation algorithm by Jeffrey Hinton. 2000 to 2010, during this particular period, there was conducted a Spinnaker project initiation. The Spinnaker means Spiking Neural Network Architecture project, launched in 2005, aimed to simulate large-scale spiking neural networks in real time. It focused on modeling spiking neuron behaviors and synaptic plasticity. The 2010 brought about significant advancement in both neuromorphic hardware and software. During 2011 to 2015, there was introduction of IBM's True North, and in 2014, IBM means International Business Machines Corporation unveiled the True North neuromorphic chip in 2014. It featured a large-scale architecture with 1 million programmable neurons and 256 million programmable synapses. And the second concept goes to advancement in spiking neural networks. Research in spiking neural networks continued to progress with a focus on synaptic plasticity, learning algorithms, and the evolution of natural circuits. During the period of 2016 to 2020, Intel's Loihi chip that was developed in 2017, Intel introduced the Loihi neuromorphic research chip. Loihi combined digital and analog circuit to mimic neural behavior. As part of this and diverse application, neuromorphic engineering found application in various fields including robotics, image and speech recognition, and edge computing. The last period goes to 2021 to early 2022. It mainly focused on edge computing and integration with the artificial intelligence and machine learning. Neuromorphic engineering represents an exciting frontier in artificial intelligence and computing. Let's move on to what is neuromorphic computing. It is an interdisciplinary field of study that involves the development of computational models and hardware architectures inspired by the structure and function of human brain. And the goal of neuromorphic engineering is to create intelligent machines that can process information in a way that is similar to how the human brain does. One key aspect of neuromorphic computing is that it is designed to be highly energy efficient. This is because the brain can perform a wide range of tasks using very little power, and neuromorphic systems aim to replicate this efficiency. This is unlike traditional computing, which is based on von Neumann systems consisting of three different units: processing unit, input output unit, and storage unit. A novel approach to computer architecture called neuromorphic computing is based on the composition and operation of biological neural networks found in the brain. It consists of a processing unit, input-output unit, and a storage unit are used in classical computing. John von Neumann originally developed neuromorphic computing, which is widely utilized in contemporary computers and is regarded as the industry standard architecture for computer systems. It is predicated on the separation of memory and processor. From the diagram, as you can see this figure shows the graphical comparison of the von Neumann and neuromorphic architecture. On the left figure, which shows the von Neumann architecture used in traditional computers, and in this figure, the red lines depict the data communication bottleneck in the von Neumann architecture, and on the right figure, it is a graphical representation of general neuromorphic architecture. In this architecture, the processing and the memory is decentralized across different neuronal units and synapses, creating a naturally parallel computing environment via the mesh-like structure. Because of their data-centric design and the frequent switching between processing and storage components, neural networks exhibit bottlenecks in their architecture. This inflexibility prompts the creation of low-power nanoscale devices that resemble synapses in order to scale neuromorphic circuits up to level of the human brain. And let's move on to the neuromorphic hardwares. A cutting-edge approach to the computer architecture called neuromorphic hardware imitates the complex structure and operation of the human brain. It builds effective and potent computing systems by utilizing ideas like distributed memory, event-driven processing, and low-power usages. Applications in robotics, artificial intelligence, machine learning, and sensory processing could benefit greatly from the novel technique, with the goal of overcoming the constraints of traditional architecture and opening up new possibilities in computational efficiency and cognitive capacities. Neuromorphic hardware is a paradigm shift in computing. As you can see this figure shows the comparison of computing architectures. In July 2019, the US Air Force Research Laboratory, in partnership with IBM, unveiled the world's largest neuromorphic digital synaptic supercomputer dubbed Blue Raven. The system delivers the equivalent of 64 million neurons and 60 billion synapses of processing power while only consuming 40 watts. And as part of this, there will be a von Neumann versus neuromorphic architecture. They have a complete separation between von Neumann computers and neuromorphic computers. Von Neumann computers consist of separate processing and memory units, binary values, and speed and energy issues. But in the case of neuromorphic hardware, collocated processing and memory, massively parallel, inherently scalable, are the major comparison between von Neumann and neuromorphic engineering. And let's dive into the topic of artificial neural network. Generally, it is called as ANN. The term artificial neural network is derived from biological neural networks that develop the structure of a human brain. The objective of ANN is to perform cognitive functions such as problem solving and machine learning. The networks are made up of nodes, connected neurons that are connected across a number of layers. ANN, adaptive resonance theory, coherent self-organization maps, building blocks, unsupervised learning, and evolutionary algorithms are some of the topics covered in this lesson. It offers a thorough comparison of the networks. The biological neural networks that give the human brain to structure are the source of the term artificial neural network. So in this figure you can see that it shows the biological neural network. A biological neural network, which includes the human brain, is a sophisticated network of interconnected neurons that serves as the foundation of the nervous system in all living things. Through electrochemical processes, these neurons transfer signals, forming an intricate network of communication. The network enables information processing and integration, resulting in the coordination of physiological and cognitive processes. It is divided into specialized sections and connected by synapses. Its amazing abilities include learning from experience, flexibility, and parallel processing. Researching these networks sheds light on the basic principles that underlies behavior, consciousness, and cognition, which motivates the creation of artificial neural networks for artificial intelligence. The given figure illustrates the typical diagram of biological neural network, and the key components are cell body, dendrites, axon, synapses, and myelin sheets. And on this slide, it is the typical artificial neural network and the mathematical representation of ANN. Computational models known as ANN are modeled after biological neural networks, and the typical artificial neural network looks something like this figure. And dendrites from biological neural network represent input in artificial neural networks. Cell nucleus represent nodes, synapse represent weights, and axon represent output. As compared between biological network and the artificial neural network, in the term dendrite from the biological neural network represent the inputs as the artificial neural network, and cell nucleus of the biological neural networks is the same function in artificial neural network in the form of nodes, and synapses from the biological neural network is referred to as the same in the artificial network as weights, and axon as output. From the figure we can see that there is a lot of input. 1 input, 2 input, 3 are emerging to the neuron by means of weight w1, w2, wn, and which is combined into the neuron and goes output as y. And there are around 1,000 billion neurons in the human brain, and each neuron has an association point somewhere in the range of 1,000 and 10,000. In the human brain, data is stored in such a manner as to be distributed, and we can extract more than one piece of this data when necessary from our memory parallelly. Let's move on to the next slide. These are the works related basis on the neuromorphic engineering. Additionally, the investigate software and the neuromorphic techniques for machine learning, model optimization, and computation efficiency. These endeavors exhibit potential for utilization in artificial intelligence, robotics, and sensory processing domains. And as you can see, these are the work related. First one is Blue Raven, which means the Air Force's research laboratory, in partnership with IBM, unveiled the world's largest neuromorphic digital synaptic supercomputer in July 2019, dubbed Blue Raven, at AFRL's Information Directorate Advanced Computing Application Lab in Rome, New York. Today, challenges exist in the mobile and autonomous realms due to the limiting factors of size, weight, and power of computing devices, commonly referred to as SWAP. The experimental Blue Raven, with its end-to-end IBM TrueNode ecosystem, will aim to improve on that state of the art by delivering the equivalent of 64 million neurons and 60 billion synapses of processing power, while only consuming 40 watts, equivalent to the household light hub. And the second works related to Spinnaker project at the University of Manchester. A pioneering effort of neuromorphic engineering, the University of Manchester's Spinnaker project seeks to create a massively parallel computing platform model after the neural networks found in the human brain. In order to mimic a large number of simple spiking neurons and their connections, the research makes us use to specially constructed hardware with thousands of ARM processors. Spinnaker uses an event-driven design in contrast to conventional von-Neumann architecture, allocating memory and processing sources throughout its network. Large-scale neural network modeling and simulations are well suited to this design since it allows for effective parallel processing. And in order to say this, Spinnaker is a novel, massively parallel computer architecture inspired by the fundamental structure and function of the human brain, which itself is composed of billions of simple computing elements communicated using unreliable spikes. Next work is Brainscale project at the University of Heidelberg. The research project brain-inspired multi-scale computation in neuromorphic hybrid system was financed by EU FET Proactive FP7. The project was completed on March 31, 2015, having begun on January 1, 2011. 90 research groups from 10 different European nations worked together on it. The Human Brain Project on the Neuromorphic Computer platform continues the hardware development for the neuromorphic computer system. The goal of the Brainscale project is to comprehend and model how various spatial and temporal scales interact during brain information processing. It focuses on spatial scales from individual neurons to entire functional brain areas and a temporal range from milliseconds to hours or day, utilizing both computational analysis and in vivo biological experimentation. And the last work is related to Intel Labs Lohi 2. Lohi 2 Lohi 2 is the successor to Lohi, a second generation neuromorphic research test chip designed by Intel Labs that was introduced in late 2021. The chip uses asynchronous spiking neural networks to implement adaptive self-modifying event-driven fine-grained parallel computation used to implement learning and inference with high efficiency. The chip is a 128 neuromorphic cores many-core IC fabricated on Intel 4 process and features a unique programmable microcode learning engine for on-chip SNN training. And the 3 years of Loi's literature. Over the past 3 years, Intel NRC members have evaluated Loi in a wide range of application demonstration. Some examples include adaptive robot arm control, visual tactile sensory perceptron, learning and recognizing new orders and gestures, fast database similarity search, etc. Then we move on to these are the figures related to these works. The first figure shows the Blue Raven neuromorphic digital synaptic supercomputers, and the second figure is related to the Spinnaker chip, and third figure is the design drawing of the Brainscale neural network hardware module using wafer scale integration. Fourth and fifth figure represent the Lohi 2 chip that released in October 2021. Let's move on to the advantages of neuromorphic engineering. Neuromorphic system offers a range of advantages over traditional computing architectures. These advantages stem from their ability to emulate the behavior of biological nervous system. The advantages are energy efficiency, bio-inspired design, parallel processing, adaptability and learning, real-time processing, and neuromorphic sensors. Energy efficiency refers to neuromorphic systems are highly energy efficient. They are designed to mimic the low power parallel processing capabilities of the human brain. And the bio-inspired design in neuromorphic engineering was drawing inspiration from the structure and functioning of biological neural system, particularly by human brain, to create more efficient and effective computation system. Parallel processing says that neuromorphic system can perform parallel processing, allowing multiple operations to occur simultaneously, and adaptability and learning can exhibit adaptive behavior and learning capabilities similar to the brain's ability to learn from experience. The last one, real-time processing, which says that the parallel and distributed nature of neuromorphic systems make them well suited for a real-time processing. This is beneficial for applications such as robotics, where quick decision making and responsiveness to the environment are crucial. Then look on to the challenges. These are the challenges of the neuromorphic engineering: scalability, hardware complexity, plasticity, and adaptation. So, while neuromorphic engineering holds great promises, there are several challenges and limitations that need to be addressed. These include complexity of the design and implementation of neuromorphic system, etc. Additionally, issues related to power consumption, scalability, and compatibility with existing technologies need to be overcome in order to fully leverage the potential of the emerging field. Scalability, which is the building large-scale neuromorphic system that can reveal the complexity of biological brains, is a significant challenge. Ensuring that the hardware and software can efficiently scale to handle increasingly large networks of neurons is a key concern. And look onto the hardware complexity. Designing neuromorphic hardware that accurately emulates the complexity of biological nervous system is a formidable task. Replicating the intricacies of synapses, dendrites, and axons in artificial system is technically challenging. And look onto the plasticity and adaptation. Emulating the synaptic plasticity and adaptability of biological synapses in artificial system is a complex task, and achieving the dynamic changes in synaptic weight that occur in biological learning process is still an area of active research. On to the application. These are the application of neuromorphic engineering, self-driving cars, robotics, artificial intelligence, and edge computing. So, self-driving computers. Self-driving computers, it can benefit from neuromorphic computing by having more efficient processing, real-time responsiveness, and improved decision-making capabilities. A neuromorphic system can process a large amount of sensory data in real time and make decisions based on that data in a more efficient manner. Robotics can benefit from neuromorphic computing by having more efficient processing, real-time responsiveness, and dynamic adaptability. Neuromorphic systems are designed to operate in real time and use minimal power, make them ideal of robotic application where power and processing resources are limited. And edge computing. Neuromorphic processors are being explored for edge computing applications and enabling real-time processing of data at source, and is valuable in applications like IoT devices and smart sensors. Artificial intelligence, which is neuromorphic systems, are well suited for AI application, and they excel in tasks like image and speech recognition, natural language processing, and machine learning. These are the companies involved in neuromorphic engineering. This diagram shows that the neuromorphic chip market study period during 2018 to till 2028, as in the term of USD billions. Market size in 2023 USD 0.08 billion, and it will be increased when we reach on the year 2028 as 2.85 billion, and the largest market is North America. The main companies include Neuromorphic Engineering or IBM, Intel, Samsung Electronics, SKH Hynix, HRL Laboratories LLCs. These are the future scope of neuromorphic engineering: advanced artificial intelligence, edge computing and IoT, brain-machine interfaces, neuromorphic vision and hearing system. As part of this, there is lot of future in neuromorphic engineering because it is the currently trend topic, and it will be a huge possibility to increase its contribution, and it will lead to a very large possibilities to develop a new world. And advancement of artificial intelligence shows the significantly enhanced the capabilities of artificial intelligence, and neuromorphic vision and hearing system shows will revolutionize sensory processing. These are the references that used for this seminar. So, in the conclusion, the goal of the exciting field of neuromorphic computing is to build the computers that are smarter, quicker, and more efficient. One of its primary benefits over traditional computers is that it can process data in parallel, which increases efficiency and reduces power consumption. In addition, it can handle massive volumes of data in real time, which makes it perfect for applications like natural language processing, autonomous systems, and picture and audio recognition. These capabilities have the potential to have a big influence on the transportation, finance, and healthcare sectors. However, there are a number of difficulties with the neuromorphic computing, such as limited hardware and software support due to the scarcity of commercial neuromorphic computer systems, which are frequently pricey and challenging to operate. Furthermore, since creating software of these devices requires a variety of methodologies and no widely recognized methodology, there is no standard programming paradigm and for neuromorphic computing. For neuromorphic computing to reach its fully potential across multiple industries, these issues must be resolved. Despite these challenges, the future of neuromorphic engineering looks promising with many exciting advancements expected. Thank you.